So far, we considered isolated systems in which we defined the number of particles, the energy, and the volume. In the following, we will extend our description by assuming that this isolated system is now placed in a reservoir and the energy between the system and the reservoir is freely exchanged. The situation is described by the canonical ensemble. The assumption in the canonical ensemble is that the reservoir, which is much bigger than the system itself, is described in the microcanonical ensemble. In this situation, the total energy is given by the sum of the energy of the reservoir plus the energy of the system. Thereby, the energy of the reservoir is assumed to be much bigger than the energy of the system. Now what we can calculate is the probability to find the system at the given energy E. The probability of the system to be at energy E equals the probability that the reservoir has an energy, the total energy minus E. Now the reservoir we describe in the microcanonical ensemble, hence this probability is just given by the ratio of the partition functions of the reservoir at the energies Et minus E and Et, or with the definition of the entropy by the ratio of the two exponential functions. Now we consider the entropy of the reservoir at energy Et minus T, with the assumption that the energy E is much smaller than the total energy. We use the Taylor expansion for the entropy, reading the entropy of the reservoir at Et minus the derivative of the entropy by the energy times E. Now this partial derivative with respect to E we defined as beta, the inverse temperature. Hence, the entropy of the reservoir at this difference energy is just given by the entropy of the reservoir at Et minus beta E. Now using our prior definition of the probability of the system to be at energy E, the probability is proportional to E to the minus beta E. The proportionality factor we obtain from the normalization of P, which is the partition function of the canonical ensemble, Z given by the sum on all states, E to the minus beta E. We see that in this definition, Z now depends on the number of particles n, the inverse temperature beta, and the volume. A likewise definition we can do in the classical sense using the phase space integral that we considered earlier. As for the microcanonical ensemble, we define the thermodynamic potential phi that is a function of n, beta, and v. The canonical ensemble is directly proportional to the free energy, the description that is given in the book. The free energy is a function of the number of particles, the temperature, and the volume, and equals to minus kBt times the log of the canonical partition function z. We saw for the microcanonical ensemble that the derivatives of the log of the partition functions describes the equilibrium condition of the system. Let's do these partial derivatives. And we start with a partial derivative with respect to the inverse temperature beta. By taking this derivative from the exponential, we obtain the prefactor minus e, by which the sum simply is the definition of the mean of a minus e. So we obtain that the partial derivative of ln z is minus the mean energy of the system. We just saw that the partial derivative of the log of the partition function yields the mean of an observable. This is a very general strategy that we will come back to later and call the log derivative trick. Now let's consider the partial derivative of the log of the partition function with respect to v. For that we look back to the Taylor expansion that we did earlier, leading to the expression that we have to consider the partial derivative with respect to the volume of S of n, E, and V minus beta E. Yet we have to consider here that now the energy is not a free parameter, but is again dependent on n, beta, and v. We can cope with this difficulty by first taking the partial derivative with respect to e and then multiplying by the partial derivative of e with respect to v. We see that by doing the partial derivatives, the last term will vanish, and we obtain that the partial derivative of the log of the partition function with respect to e is equal to beta p, or equal to the compressibility gamma, which is exactly the same as we found for the microcanonical ensemble. Likewise, we would have to do the same trick when we consider the partial derivative of the log of the partition function with respect to the number of particles n, and we obtain that this is equal to the affinity alpha, or equal to minus beta mu. Now for the canonical ensemble, the system can interchange energy with its surrounding. We have shown how we can calculate now the mean energy, but how well is the mean energy defined? For that, we consider the variance in the mean energy, which we obtain from the definition of the variance as the mean squared energy minus the mean energy squared. The mean squared energy is related to the second partial derivative of the partition function with respect to beta, and the mean energy is given by the first derivative of the partition function with respect to beta. Now, rearranging these partial derivatives, we obtain that the variance is given by minus partial derivative of the mean energy by d beta. Or by changing variables to the temperature and not the inverse temperature, we finally obtain that the variance in E is given by Kb times the specific heat Cv T squared, where Cv is partial derivative of the energy with respect to the temperature. Now coming back out to our question was, how well defined is the energy? So what we have to consider is, what is the ratio between delta E and E? Now we saw that the variance scales with the specific heat of the system. Now if we redefine the specific heat for a single particle, that means delta E now scales with the square root of n times the Cv, where C here is now in small letters, meaning the specific heat of a single particle. And that has to be divided by n times the mean energy per particle. So what we find is that the relative width of the distribution of the mean energy scales like 1 divided by square root of n times some molecular parameters like the specific heat for a single particle and the single particle energy. And again, as we would expect from the law of large numbers, if n goes to infinity, the width of the distribution goes to 0. Hence, what we learned is that actually fluctuations in the mean energy just vanish. We also could interpret it in this way, saying that the canonical ensemble, as we derived here, is a very good approximation for the microcanonical ensemble, where we had to fix the energy of the system. Second, what we learned is that the specific heat is an important parameter that relates the fluctuations in the observable mean E. Now to summarize, so we derived the expressions for the canonical ensemble describing the situation where the system is embedded in a thermal bath. The partition function, the Z, now depends on the number of particles, the temperature of the bath, and the volume is given by the sum on all states, k, e to the minus beta ek. Further, we looked into the derivatives of the thermodynamic potential, and we found that the derivative of the log of z with respect to the number of particles yields the chemical potential minus beta mu. For the derivative with respect to beta, we obtain minus the mean energy, And for the derivative with respect to V, we obtain beta p as for the microcanonical ensemble.